Willing to spend an ATP if what? If you know you're going to get more by the end of the process. See, you've heard the old adage, it takes money to make money. I've never had a chance to try that out, but they tell me it's true. I've invested everything I've gotten from Rocky Mountain Creation Fellowship, but that hadn't helped a whole lot. But here's an investment, okay? And so notice, by the way, that what we're looking at here is one of the characteristics of a created system that is absent totally from evolved systems. We're looking at anticipation, okay? And sometimes people ask us that, how can you tell whether a system has been evolved or whether it's been created? And there's several marks of a created system that will be absent from an evolved system. And one is anticipation, looking to the future. And so that's what you're doing here. Now, I think I even mentioned this on the program. I almost had 100 average in biology as a student. I was really into biology. But I got -2 on one of my essays because I wrote something like living plants have this enzyme in order to. You know, I inferred that they had a purpose, that they had this enzyme to accomplish a goal, and the prof marked -2, teleology in the margin. You know, they were so into evolution at this college to even suggest inadvertently that there might be a purpose was a no-no. You know, evolution's blind. What is Dawkins from England, you know, evolution is the, quote, blind watchmaker. There are no goals, there are no looking ahead, and yet evolution can't ever do this step. Because you're not going to spend this without knowing that there's a return later on. You've just made life less possible than it was a few moments ago. You've used up some energy that could have been used, you know, for instance, to make a nerve work or muscle or something like that. And now all you've gotten is just sugar with a phosphate stuck on it that's still no good for anything and still won't explode. And so this anticipation is one of these remarks, and you see it in the next step. Okay, now you've got glucose 6-phosphate, and the 6 just means it's attached to the 6th carbon. What did that do for you? And the answer is absolutely nothing. You just wasted a perfectly good energy molecule, accomplished nothing at the moment. You accomplished nothing in this step. Okay, all you're doing is setting up the next step. So you got to plan ahead. Now, if you're designing a factory to produce a product, you don't care if you use some energy back here because you know you're going to get it back later on. Well, the next step is even worse. Oh, by the way, the kind of enzyme used here, and we'll see this over and over again, is a kinase. It's just an enzyme, a big protein that can grab other molecules and hold them for speedy reaction. And the enzymes that use ATP are called kinases, and this is a fairly general one, hexose kinase. It'll act on any 6-carbon sugar to add phosphate to it. Well, the next step, then now you've got glucose 6-phosphate. The second step, it just changes shape. It was a 6-sided ring, and it changes into a 5-sided ring that leaves another carbon sticking up out here. And so the kind of enzyme that does that is an isomerase. And an isomer is a form of a molecule that looks, two forms of a molecule that have the same parts arranged differently. And enzymes that do that are called isomerases. And so isomer, like C6H12O6, there are actually 32 different molecules that have that formula, same parts arranged in different ways. Well, organic chemists, you know, chemists that work with the chemistry of human beings, are just totally amazed. To do this reaction in the chemistry lab takes all kinds of things that one protein can grab, twist, and you get the reaction right away. But notice, by the way, what did that do for you? And the answer is absolutely nothing. And so far, you got step 1 and step 2. You better have some plan in mind because now you're making things happen that, you know, aren't really getting you anywhere. There's no way these things can be built up in the population by natural selection. And then to make matters worse, on the third step, now that you've turned it into a 5-carbon sugar, what you've done, now you got carbon fingers sticking out in both directions. So you get the kinase back again, a different one, phosphofructo kinase here that will add another ATP. Now notice at this point, you've spent 2 molecules of ATP and you've got nothing to show for it. You have a 5-carbon sugar with phosphates dangling off each side. That molecule doesn't do a thing in living cells. And so there's really nothing you can say. There's no selective advantage. No selective advantage you can refer to. And evolutionists get away with murder just by saying selective advantage. That's what it happens. I had students from ICR at the San Diego Zoo this summer, and we were looking at the flamingos. And I can't demonstrate this, of course, but the flamingos were standing on one leg. But some of you know this. When they stand on one leg, what looks like their knee is bent in the opposite direction from us. And you look at that, and it looks like, like I say, I can't even hardly straighten it out anyway, but I certainly can't bend it up the other way. And so I was talking to the students, why do you suppose the flamingo bends its knee in the opposite direction? And there was a tourist there that had a ready answer. British accent and everything, fresh from watching a Richard Dawkins special, on evolution. He says the key is selective advantage. Always remember it's selective advantage. And I said, no, the key is that's not a knee, it's an ankle. Oh. and so actually the flamingo's knee is way up here, under his feathers. So he just got an ankle that goes way up, to where our knee would be. So he just walked away. So some discussions are shorter than others. But now here we've taken, 3 sophisticated protein enzymes. We've used up 2 molecules of the energy we wanted to make. And all we've got is a molecule that looks like this, a 5-sided thing with 2 phosphates on the side. What's the point of all that? Well, this molecule splits in half. What it did, the phosphate group, that circle P actually stands for P double bond O, OH, 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 if you drew in everything. And so these are big groups that are very reactive chemically. So you got this little 5-carbon sugar or 5-ring sugar, with these 2 big groups attached, and it splits. And originally I was going to draw this all out, one step at a time, but this way I can say more if I just tell you this. It splits into 2 halves, and at first the 2 halves look like this. And so it looks like they're unequal, but actually what happens is that a hydrogen shifts down here and here, and this molecule spontaneously converts to this one, and so you split 1 6-carbon sugar into 2 3-carbon sugars. And so that's what you've got down here is a C3 just means there's 3 carbons in it. So we